Hey everyone, if we go far into the intergalactic space, we encounter one of the most emptiest corners of the universe. As empty as it might seem, it's not completely empty. There's roughly a quarter of a hydrogen atom per cubic meter. A quarter of a hydrogen atom per cubic meter? Well, welcome to the intergalactic medium. For comparison, interstellar space, so space between stars, has a density of roughly 4 hydrogen atoms per centimeter cube. So a difference of 6 orders of magnitudes. Well, that's some insane emptiness. For a little bit more groundedness, take LHC. It's the most artificial vacuum that we've created, but that only takes us to 10 to the 6 molecules per centimeter cube. Numbers speak for themselves. Now the universe is expanding and cooling, and entropy is on its continuous rise. So places like this in the intergalactic medium, or IGM for short, are probably among the emptiest the universe has ever been. With all of this, it may seem like as scary as this place is, it is so scarce that it would be of little relevance to anyone. But that's just not true. Even though it is quite empty, it is big. It is like 99% of the universe's volume. So when there's that much space available, things start to add up. You may have seen the pie chart decomposition of the universe, according to which the normal matter, the things that we can see, make up only 5% of the universe's total energy budget, which seems small to harbor everything that we can see out there. And yet, most of this normal matter does not make up any stars or galaxies. Rather, roughly 80% of this normal matter exists in the form of diffused, extremely low density gas forming the intergalactic medium. Indeed, the most emptiest parts of the universe contain most of it. And that just tells us how big of a volume the universe truly is. Galaxies have high concentration of matter, but they're not the norm. Until about some decades ago, there was this mystery around the missing baryons. Now, baryons are particles with 3 quarks, so like proton and neutron, they are baryons. We sort of have a theory for how things probably turned out in the early universe. Among other things, that theory gives us the ratio of the normal matter to photons that we should expect in our universe. We have the cosmic microwave background, which somehow, someway gives us the number of photons, and so we do have an estimate for how much normal matter we should expect in our universe. So here's the thing. All the stars and everything in and around the galaxy only makes up roughly 20% of this number. And that's sort of a problem. Most of the normal matter is hidden, and we don't know where. This is baryons and where to find them. Now, how do we see something that isn't giving off enough light to be detected? Well, you shine light to it. Well, of course, that's exactly what we did in a bit more glorious way. As light sources, we used quasars, so literally the most luminous objects in the universe. These are black holes with an accretion disk bright enough to outshine entire galaxies. The light coming from these quasars traveled through empty space through the intergalactic medium and reached us. So any matter in between would interact with it. And matter leaves its trace on light. When light encounters a lone hydrogen atom present in the intergalactic medium, the hydrogen atom absorbs the light at a particular wavelength known as the Lyman-alpha. If we split this light here on Earth, we would see a signature of this absorbance. Now, in a static universe, we would see a spike at that particular wavelength that corresponds to the Lyman-alpha. However, our universe is expanding, and so things further away are moving away from us faster, and so we see a sort of a Doppler effect. Wavelength that we do observe here on Earth depends upon the redshift of the hydrogen atom, so the distance of that event from here. Which means here on Earth, what we see on screens is like a distribution spread across a range of wavelengths, a conclusive evidence of there being continuous matter in the intergalactic medium. There's one little catch though. Even after accounting for this, we could only get to half the expected number of baryons. Half the universe was still missing. Wait, why? Where's the rest of the matter then? Well, it's also in the IGM, just not in the way we expected. There's something that we must have missed. After the Big Bang, the universe continued to expand and cool. As that happened, the conditions evolved to allow for the formation of the first nuclei. Around 400,000 years later, as things further cooled, we saw the formation of neutral atoms. Since that point, the universe had been filled with this neutral gas of mostly hydrogen and helium. But that was bound to change. After a while though, for now, gravity was doing its thing. The tiny inhomogeneities in the distribution of matter, and mostly dark matter, led to the formation of gravity hotspots, local centers of gravity that attracted regular old matter, acting as seeds for the formation of the first stars and galaxies in the universe. Things were evolving. A lot more slower though. It took some hundreds of million years for the first stars to form. These first stars, also known as population 3 stars, were special in that they were composed almost entirely of hydrogen and helium, with virtually no heavier elements. They were massive and short-lived and led to a drastic change. Since the beginning, it was the first time that new light had entered the cosmos. This starlight was energetic enough to ionize the neutral media that had previously been formed, leading to the epoch of reionization. Fast forward to now, there's a whole lot of matter in the IgM that we didn't observe in the Lyman-alpha absorption spectrum. Ionized matter wouldn't give the same Lyman-alpha transition, would it? Yes. The Lyman-alpha wavelength is the characteristic for the ground state to excited state transition in a neutral hydrogen atom, not for ionized media. So in regions without enough regular neutral hydrogen atom, Lyman-alpha won't really give us a lot about the presence of matter. Looking at the universe, our attention goes directly to where the glowing stuff is. Galaxies. Galaxies, in addition to having regular matter, also have this invisible form of dark matter, usually in far excessive amounts, leading to the formation of dark matter halos. So from this high density region and moving to the intergalactic less density region, we see a kind of a gradient. As we move away, we encounter less and less regular matter and feel the presence of one more invisible gravity, dark matter. Eventually, we reach something that's called the Circumgalactic Medium. It is kind of like the IgM, but not quite, because it still has a lot more influence from and over to a nearby galaxy. It controls the formation of stars. The flow of material in and out of the galaxy directly affects how many and which kind of stars would form. But for now, as we move away, we get to the WHIM. WHIM is short for Warm-Hot Intergalactic Medium. It's a medium composed almost entirely of highly ionized diffuse gas. It's called the WHIM because the particles here have temperatures higher than at the IgM. And here you can have a laugh, as by warm and hot we mean temperatures of 10 to the 5 to 10 to the 7 kelvins respectively. Even though it seems like a million degrees would be scorching hot, remember that the densities here are quite low, and so it would most certainly be freezing cold. Pack sweaters. Hydrodynamic simulations of the universe show that roughly half the regular matter exists in the WHIM. Also, FRB dispersions done in the last decade suggest the presence of highly ionized matter in the WHIM. FRBs are highly energetic pulses of radio emissions, the sources of which we are not completely aware of. Yet these radio emissions get affected by the presence of ionized matter in the WHIM, getting dispersed. The way and amount in which they get dispersed then allows us to map the presence of matter in the WHIM. So, mystery solved, I guess? Yes, for now. Though there are other things to look forward to, unsolved problems that seem so far and yet someday be solved. Subscribe if you want to keep up with us. Like if you think it was worth it. Tell me your thoughts in the comments, and I shall see you in the next one. Thanks for watching.